Q A mu. A mu is the gauge field, which in principle has 4 components, and then this is the kinetic term of the abelian gauge field, which is F mu nu. F mu nu, where F mu nu is the field strength, partial of mu A of mu minus partial of mu A of mu, and this is the potential, which in principle will only depend on the absolute value of the scalar field amplitude, of the complex scalar field amplitude. Okay, so this is an abelian fixed model, and this is what we are gonna learn how to simulate in the lattice. And this field will evolve in the universe in such a way that the scale factor evolves self-consistently. So we will evolve this field together with the Riemann equation, as we did for the scalar example this morning. G of A is the, I think I specified later, but G of A is the coupling strength, and Q of A is the charge. This is we are going to consider model 1. Model 2 is precisely what we will cover in lecture 10, in which Johannes and Ander will discuss how to simulate gauge field coupled to actions, where the interaction between the gauge field and the scalar field, or that is the action in this case, is different, right? Here the coupling is the coupling between the complex scalar and the abelian gauge field is in the covariant derivative here, right? While in the axionic case, you have a coupling which is F mu dual phi. So I will let him discuss this in more detail on Friday. And in this lecture, I will focus on the U1 gate, and in lecture 7 tomorrow, Adrian will focus in the similar scenario where the complex scalar is coupled to SU2 field. And okay, so this is the table of content of my presentation. I will start by describing the equations of motion in the continuum. Then I will talk a bit about gauge invariance in the lattice and how we can use links and plaquettes to preserve this, to preserve the gauge invariance. Then I will talk about how we implement the gauge fields in CosmoLattice, and then I will show an example. So let's start with the equations of motion. So we are going to learn how to simulate in the lattice the following action. This is the same action as before. I have just included for completeness a scalar singlet phi. Okay? This is a complex scalar, this is a singlet, and the potential will depend on the scalar field that you include in this here. In this case, will depend on phi and the absolute value of the complex scalar. So this is what I was saying. Phi is a scalar singlet. Curly phi is a complex scalar, which depends on on 2 components, phi 0 and phi 1, which are real. So this is complex. Then this is the covariant derivative, where GA is the gauge coupling and QA is the abelian charge. Basically, how the different scalars, this sets how different scalars are coupled to the gauge field. This is the field strength. And then from a field strength, we can build the electric field, which is the 0I component of the field strength, and the magnetic field, right? Which is, for example, we have both of these vectors, both of these quantities have 3 components, right? I goes from 1, 2, and 3. So this is a 3 vector, this is a 3 vector. And how many fields we evolve here? We need to evolve 6 fields, right? The scalar singlet, phi, the 2 components of the complex scalar, and then we are gonna only evolve 3 of the 4 components of the abelian gauge field, right? Because we are gonna work, CosmoLattice works in the temporal gauge in which A0 is 0 always. So we will have just 6 fields to evolve, or 6 field components to evolve.
Paco, sorry, there is another question by Sayak. Sayak, please go ahead.
Hello, can you hear me?
Yes, I can hear you.
So in the action, the first kinetic term of the phi, that shouldn't be that d mu covariant derivative.
So can you repeat? I haven't heard you well. In the covariant derivative, what?
The first term in the action. That is, you write del mu phi, Shouldn't it
Phi
be
mu-
d
You mean
in
here?
the action?
In the action.
In the action.
In the
action.
action.
Mhm.
So what's the problem
So-
here? Sorry.
The first term, that is del mu phi.
Yeah. What's the problem with this?
Del mu, the first del mu phi. So that should be d mu phi, isn't it?
No, I think
Covariant.
this is correct, right?
No, not this term, the first term.
This one.
Yes.
This one. What I think this is right.
What's the problem?
This should be, that should be covariant derivative d mu.
No, because this is a scalar singlet. This is not a complex. This is not a complex scalar. It's a scalar singlet, which is not coupled to the gauge field directly.
Okay.
Only this one is coupled to the gauge field to the covariant derivative.
Okay.
So phi and curly phi are different kind of field species. Hey, very well. So we have the action here. We can minimize the action and obtain the equation of motion in a flat space-time. We have the equation of the scalar singlet that we know very well. Then the equation of the complex scalar, which is very similar. It's solved by the derivative of the potential with respect to the modulus of phi. And then we have the equation for the U1 gauge field, right? When this is the U1 current, right? The gauge fields are stored by the current which takes this one. So what is important here is that both the action and the equations of motion are invariant under gauge transformations, right? And basically, we take this field phi and we multiply it by e to the minus the I, the constant alpha fixed, where alpha fixed is an arbitrary function, and simultaneously we shift the gauge field that get the same gauge field minus the partial of mu alpha fixed. Then we see that both the action and the equation of motion are invariant under this term. Okay? This is seen typically in a first year quantum field theory course. And this is done like this, like we can see that in the continuum, the gauge invariance is preserved. Just an important comment, the field strength is gauge invariant. So A of mu is not gauge invariant, so it is not physical. The quantity that is physical is the F mu, because you can see that it's gauge invariant. All right. So this means that the electric field and magnetic field, which are given by the field strength, these are also gauge invariant quantities. So basically, you will see that when we obtain observables for the gauge field, we will always build them in terms of gauge invariant quantity. We will, for example, in CosmoLattice, we do not plot the evolution of a particular gauge field component because this means nothing. This is gauge dependent. What we plot, for example, is the average of the electric field, the average of the magnetic field. Let's include expansion of the universe. We are going to write the Feynman-Robertson-Walker metric in alpha time. So you have a to the 2 alpha here. Remember, alpha equals 0 is cosmic time. Alpha equals 1 is conformal time. So this time includes both cases, depending on the choice of alpha you have. And these are the equations of motion in the continuum, including the space factor. These are the dynamical equations of motion. This one, so we have the equation of motion of the scalar singlet and the complex scalar, which in reality is on two equations, two independent equations, because phi is complex here. And then we have the equation of motion of the gauge field, right, where they are solved by the current that they have there. Right? Note that these are really three equations because I goes from 1 to 3, right? And you can write also the equations for each of the gauge field components independently. And note, by the way, that they are like these equations here, the equations of the component, are very similar qualitatively to the equations of motion of the scalar field, right? What the difference is basically, well, these are sourced by the current instead of by the derivative of the potential. you have here a different friction term, which goes as 1 minus alpha instead of 3 minus alpha. And then you have this cross term here, which is not in the scalar field equation. But this already is giving us a hint of how to discretize or how to evolve this equation. Right? It will be in a very similar way to the ones of the scalar field. And then there is another equation, which is the Gauge constraint, which must be preserved at all times. This is not a dynamical equation. This is a constraint, right, that we can use to check. So if we solve the equations of this equation in the continuum, it will be preserved always, right? That's why it is a constraint. But also we can use it to monitor how well our simulation is going in the lattice, as we said. So what does this mean? Well, remember that F0i is the electric field, so we can write this equation as the gradient of the on the left-hand side. We can write it as the gradient, sorry, as the divergence of the electric field. And this is equal to the zero term of the curve. Let's now integrate in volume both sides, right? And then using the Gauge theorem, we can write the integral over the volume of this as the integral over the surface of e to ds, right? And this is going to be equal to a squared, the integral of the current over the entire volume, which in this case is going to be the lattice. This is the electric charge, and it's constant. And what we're going to do is to set this to 0. We will see, we'll see later how, but we will set the electric charge, the total electric charge of the lattice to be 0. I will see later how. We can also build the storage energy tensor from the Lagrangian in a very similar way. It's this complicated expression. And now from here, we can identify the energy density and the pressure density. And they take this one, right? The energy density includes, of course, the kinetic contribution of both scalar fields, the gradient contribution of both scalar fields, and what we call the kinetic and gradient contribution of the abelian gauge field by analogy, but note that what we call kinetic energy of the abelian sector is just the electric energy, and what we call gradient of the U1 sector is basically the magnetic energy. Okay? You have here all the definitions, and the pressure it's the same as before for the scalar field, and includes also, sorry, kinetic minus 1/3 gradient minus potential for the scalar sector, but also includes a plus 1/3 electric plus magnetic energy. Right? So we have seven different energy components. And then, of course, we can just plug the energy density and the pressure in the Riemann equations and use these equations to solve self-consistently for the expansion of the universe. So I think let's move now to the next section, in which I want to discuss how to preserve gauge invariance in the lattice, and this will also be our first introduction to lattice gauge invariant techniques. So this is I think the key part of this lecture. So I will try to go slow. Please ask us any questions that you might have. So basically, in lecture 4, we this morning what we did was to discretize the equations of motion of the scalar field by approximating the derivatives in the continuum by finite differences in the discrete. So, for example, we had this continuous derivative of phi, and we basically what we did. In fact, I did in lesson 1. What I did was to approximate this continuous derivative by this discrete derivative, right? This is the chart, discrete derivative that I introduced, and we show that this recovers the continuum up to second-order errors in Tan-Stefan lattice spacing. Okay, so this simplifies our way of. So this is the way of discretizing the scalar singlet. But the question is now, can we do the same for gauge field? And the answer is no, because the formulation this formulation will not preserve gauge imbalance in the lattice and propagate the spurious degrees of freedom. Let's see why. This is the action in the continuum. Okay. And let's focus on the kinetic term of the complex scalar. And let's do a gauge transformation in the continuum, right? If we do this gauge transformation of phi and 8 mu, this term of the action must be gauge invariant, right? That's the reason why the kinetic term is written in such a way. So let's take the gauge, the covariant derivative of phi, and we can apply the gauge transformation. We change phi according to this prescription. We change 8 mu according to this prescription, right? And let's expand this derivative here, and we can see that this generates a minus IE term that cancels with this term generated by the gauge field, right? So basically, there is this cancellation, and then we have that this covariant derivative transforms, and the gauge transformation incorporates this exponential of minus IE alpha x. So basically, this shows that then if we do the same for the conjugate, this will generate that e to the I to the plus I e alpha x, and then they will cancel in the term, and then we show that it is the same gauge invariant. Let's try now to do a naive gauge discretization of this term, in which basically we change this continuous derivative by this discretized derivative. Can we do the same? No, we cannot do the same because they do not like this term. Because for this term, we cannot apply the Leibniz rule. Okay? The Leibniz rule means that the derivative of two functions, or the product of two functions, is the first function derivative of the second function plus the derivative of the second function of the first function second function. So this does not apply for finite difference operators, and then there is no this magic cancellation that gives you that the covariant derivative transforms with an exponential term. So if we do this type of discretization of the action, well, this is not gauge invariant. So how we do this? Let me drink some water. So how we do this? Well, the idea is to introduce what we call links and plaquettes, right? And this will ensure that we preserve gauge invariance in the lattice. So let me introduce the concept of parallel transporter, which connects 2 points of spacetime. Okay? So let me call dx mu to the 4 vector composed of the time step and the different lattice spacings. So we define the parallel transporter as the exponential of minus IE and the integral between two space-time points x and y of the gauge field. All right. Here I have included the P, means path order. For abelian gauge fields, it does nothing. It's only relevant for non-abelian gauge fields, as I guess Adrian will show you tomorrow. So you can ignore this P and just consider this parallel transporter to be the exponential of this integral here. So the reason why we introduce this parallel transporter is that you can show that it transforms under gauge transformation in this way. It basically, when you do this gauge transformation of the gauge field, then this parallel transporter includes, the only thing that does is to include this exponential term that depends on alpha x and alpha y. Where alpha x is the transformation of the gauge field A mu, and alpha y is in the transformation of alpha mu y. This will be a convenient property, and we shall see. So basically, this parallel transporter connects arbitrary points on the lattice. Let me define the links, which are basically the minimal connectors or the minimal parallel transporters. And we have two kinds of links: the B0 link and BI link, the B0 line link connects the point in which you are, x of n, right? This label here, with x of n plus 0, where 0 is the unit vector in the time direction. All right. So basically, this connects two neighbor points throughout the same time. This connects two times, 2 points, two space-time points that are at different times, but at the same spatial position. And then we have BIN, which is the same, but is the minimal connector between the point in which you are and the point in which you are plus dx. And B0 includes the A0 gauge component here, BI includes the AEI component here. This is an integral, but then this can be approximated by the exponential function of A0 and the exponential function of AI. And as links, so the links defined in this way and gauge fields live naturally at points which are located between nodes of the lattice. So at n plus mu over 2 points, right? Why? Because as we are integrated with the point in n and n plus dt, or here we are integrated with the point n and n plus dx, well, naturally, these gauge fields and these links live between points of the lattice. Okay? So let's see an example. Okay, these are 4 points of the lattice. In the horizontal direction, we have time. In the vertical direction, we have space. This is the time step, and this is the lattice space. So I have realized that here I have change notation. This should be Bn of 0, and this should be Bn of I, right, to match this figure. Well, in any case, no, this minimal connector, so this B0 link lives here in the middle, no, between, and then BI lives here. Okay.
Paco, can I make a small appreciation, a small clarification?
Yes.
It's true we normally consider they live there, but this is a convention. I mean, it's a representation in order to understand how our discretized system flows to the continuum. The link, after all, is nothing else but something connecting 2 points, no, to lattice sides. And then for symmetry reasons, no, we think of them as you said, living in the middle, no, but it's not like it's mandatory or otherwise a system fails or whatever, at the end it's a connector between 2 lattice sides, let them be in time or space, and it's very convenient actually to understand the flow to the continuum to ascribe them as living in the middle. Okay.
Okay, thank you. So now let me introduce notation for links. Okay. Let's introduce notation for links. The first thing that we are gonna do is to remove the lattice side label n of the links, right? So Bn of mu, which is defined as n plus 1/2 of mu, we are gonna just remove the n, right? This is gonna be implicit, and we are gonna just call this link B mu, right? So this link here is B mu, this link here is B mu. Then we are gonna call the links that are displaced with respect these coordinates, right, with the plus minus nu notation. So B mu plus minus nu, this is gonna be the link B mu evaluated at n plus 1/2 mu plus minus nu. Okay. So for example, this link is gonna live here. It's like we take B mu and then we push it 1 direction towards the x nu. And then we are also define B of minus mu, right, as the complex conjugate of the link B mu minus mu, which is B mu evaluated at n minus 1/2 of mu. So this link is gonna live here, right? So so this is I think this is hard to explain, but it's something that if you want to do gauge theories, you need to think about and plot and to understand where the different links are defined. But hopefully I've been able to explain this. So now I ask you two questions. One question, which is if we have a link here, and if we have a link here, how are these written? So this one, it's like this one is like taking v of nu and pushing it one step towards the x mu direction, right? So this is gonna be v of mu, okay? Right? And then this one, it's like taking v minus mu and pushing it towards the new direction. So this is going to be v of minus mu b. So v of minus mu nu. So another important comment is that the conjugate operation sets up the direction in which the link is going. Okay? Because if you write, if the link as it is defined is like it's going from the point n to the point n plus mu. So if we conjugate this, it's like going from the point n plus mu to n. Right? So for example, this link is going to go in the positive direction. This link is going to go in the positive direction. And this link is going to go in the negative direction because it's defined as the conjugate of the link. Right? So v of mu goes in this direction, v of mu goes in this direction, v of minus mu goes in the opposite direction. So, okay, having defined this, having defined the links, why are we defining the links? Well, the links, we are defining them because they allow us to construct in the lattice gauge invariant quantities. All right. So we know how under a gauge transformation, we know how the complex scalar changes, transforms, how the abelian gauge field transforms, and how the link transforms, right? So from here, we can build a gauge invariant covariant derivative for the complex scalar, which we are gonna call with a plus minus sign here, and this is gonna be defined in this way as 1 over. So the covariant derivative with respect to the direction x mu is gonna be 1 over delta of x mu v of mu phi plus mu minus phi. And why are we doing this? Then we can show that if we now take this and we expand in the lattice spacing or in time step, we can see that this lattice operator recovers the continuous covariant derivative up to second order in lattice spacing. So we can use this to just discretize any the action or the equation of motion in which this term appears. Also note that it transforms, right? And the gauge invariant as in this way, like it just and the gauge transformation, it just includes this exponential factor of I e alpha. So this is what we were looking for in order to have the term of the action, this term of the action gauge invariant. Because we have partial of mu phi conjugate, so this exponential term compensates the other term in the action. Then we can build more complex stuff. We can build more complex stuff. For example, one thing that we can build are plaquettes, which are defined as the product of 4 links. This is a product of v mu, this product of links. And you can show that this product of 4 links in the it recovers in the continuum limit this exponent of several factors multiplied by the field extent. Right? And what is this plaquette? Why is this called a plaquette? Because well, if we plot the 4 links in this lattice diagram, we can go that it's like doing a whole cycle throughout a plaquette of the lattice. This is to a minimal square of the lattice. So that's why it's called a plaquette. So B mu is like going from here to here. B mu of mu is like going from here to here. B mu of mu conjugate is like going in that direction. And then B mu conjugate is like going this direction. And we do an entire cycle. You can show that if we expand the real part of the plaquette and the imaginary part of the plaquette, we can recover up to second order the field strength. So we can use this to write the field strength term in as a gauge invariant quantity when we discretize the action. Hopefully, and you can also show that it's gauge invariant. You can also show that this plaquette is gauge invariant. So hopefully we will not. Hopefully we don't need plaquettes to implement or to discretize abelian gauge theories. Plaquettes are really needed for non-abelian ones. But I guess Adrien will discuss about this in more detail in his talk tomorrow.
Can I make a comment, Paco?
Of course.
Yeah, just in my opinion, rather than saying we don't need plaquettes, which is true, what I would really say is that, we can do an alternative formulation in the case of abelian scenario, where we skip having to write plaquettes, but we can also use plaquettes to represent abelian dynamics. I mean, it works equally well. Whereas in the non-abelian, the trick that works in abelian is not valid anymore, and then you are, in principle, always forced to use plaquettes for the kinetic terms, which we'll see with Adrien.
So basically, there are like two formulations for U1 gauge fields. One is the so-called non-compact formulation, so basically you have the non-compact formulation and the compact formulation. The non-compact formulation, the important thing, the key difference is that in the non-compact formulation, what you are evolving are the gauge field amplitudes themselves. Okay? So in the fields that we will implement in CosmoLattice, in the non-compact formulation are really the fields that we evolve. They are really this gauge field component, this A of mu. While in the compact formulation, what we evolve is not the gauge field components, but the links. So I think we will focus on the non-compact formulation.
Paco, one comment. You've been 45 minutes. Do you want to make a break, or how do you want to do?
And let me finish this, and then we do the break because it's just this slide.
Sure.
Okay. So basically, you can with everything that we have seen, we can build this U1 toolkit, right? Which basically gives you tools to discretize any gauge field, right? For example, this is in the art, so in the theory review, and I think it's also in the user manual, right? So what do we have here? The definition of the links and the plaquettes, right? We have here and the covariant derivatives. So we have definitions, basic definitions of these quantities. Then we have different expansions, okay, which allow us to write gauge invariant quantities by relating the different terms of the action or of the equation with this gauge covariant derivative and links and plaquette. And you have also expressions, other expressions that may be useful, and how the different quantities transform under gauge transformation. So, for example, here you can see a difference between quantities that you use, so transformations that you use in the compact and in the non-compact formulations. So in the non-compact formulation, this term, which is the term of the field, the gauge fields in the action, right? this is mu squared. Well, we can approximate this in terms of discrete derivatives of the gauge field, right? So this is what we will use in a non-compact formulation. However, if we were going to work in a compact formulation, then we would write these two expressions. We will approximate these two expressions with this approximation, which are built in terms of plaquette and links. And as I have note here, that SU2 theories can only be formulated with a compact formulation. We will see in lecture 7, not 6. So I think we can make the break here.
Excellent. Thank you very much, Paco. Yeah, let's take 5 minutes. Of course, if there are questions, please shoot.
Yeah. I think there were questions.
There was a comment that I already addressed in the chat, but if the person who asked it, Liresa, wants to discuss about it, please go ahead.
Sorry, why the name compact or non-compact?
Actually, I don't know. I guess. Well, I guess because it's more compact.
No, it's just because it's an exponential, you know, so a complex exponential.
Okay.
You know, so the v mu, if you want, is nothing else but the cosine of the exponent plus I times or minus I times the sine of the exponent. Okay,
yes.
So it cannot grow arbitrarily. So it's compact. Whereas the non-compact formulations, if you formulate it on the amplitude of the gauge field, you know, the amplitude of the gauge fields can take whatever value.
Okay. That's clear. Thanks.
That's the origin of the wording. I don't know if there's something more profound behind, but Yeah, maybe as a remark, even though in CosmoLattice we have only implemented the non-compact for a billion case, back in the days before we had CosmoLattice, when I was implementing my own codes, I definitely implemented both formulations, and to second order in the lattice spacing, they give pretty much the same. You know, however, the non-compact I think is much easier to interpret. How you are mimicking the continuum, and I guess that's why we went for it. Whereas in the non-abelian, we are forced in any case to the non-compact. So yeah, then one has the effort to understand how the links and plaquettes really, mimic the continuum.
Yes, I see. Thanks.
And transformation rules, no? Because at the end, the whole point of all of this is that at the lattice level, your field variables, even if everything is discretized because of discretization of space-time, still everything transforms as a gauge invariant theory. The whole point of all of this is that.
Right.
Yeah. Okay, Paco, I don't know, feel free. There is another question, sorry. Okay, you want to take it, Paco?
I cannot see it.
Okay, let me read it out loud. A question in CosmoLattice, I guess, about CosmoLattice. In order to obtain power spectrum of inflation field at the end of 60 fold of inflation, how should I choose Tmax in the code? This question implies many aspects of inflation, so I think I better postpone it, and it's not related to what we are discussing. We postpone it for the turn of questions, and then I'm happy to discuss it with you. But I think, the first point you have to understand is that with a lattice simulation, and this is not related to CosmoLattice per se, it's just the limitation of the lattice, you cannot mimic the 60 foldings of inflation. You can only solve for a finite range of foldings. Okay. So if you want, I'm happy to dwell more on this at the end of Paco's talk after the turn of questions related to the lecture or today's lectures.
Okay. So shall I continue?
I think so. Go ahead, Paco, please.
Okay, so now I think we have overcome the hardest part of this lecture, which is the definition of links and packets. Now we are going to talk about something a little easier, which is how do we implement this algorithm, these gauge field equations are implemented in CosmoLattice, and then we show an example of the Higgs model simulation. Okay, let's start with the program variables. What is in the program variables? I have already defined the program variables for space-time and the scalars. Okay? But if you then what we do is the program variable associated to the gauge field component is what we are going to rescale it not by the f star like we did for the scalars, but by omega star, which is the same rescaling as for space-time. So why are we doing this? Well, let's see the link. The link is, it has in the exponent this product of A mu and delta X mu. So basically, the link in program unit text is given exactly by the same expression, because the omega star of A mu compensates with omega star introduced by, so the omega star introduced by A delta mu compensates the one of A tilde mu, sorry, compensates the one of delta X mu. And then we define the program potential in the same way. The program potential is the original potential divided by f star squared omega star. Then let me just remove this. Then we also define the program variables associated to the field strength and the gauge covariant derivative and the current. For the field strength is the initial field strength divided by omega star squared, right? This makes sense because we are introducing an omega star in the partial derivative and an omega star in the gauge field component. And then the covariant derivative introduces an omega star, and the current has the same expression. So in that the current in program variables does not include an extra factor.
Paco, sorry, I think inside the potential with F star, the curly phi should be phi tilde, right?
Curly.
On the right hand side, yeah.
Here?
Yes.
Yes. Yes, you are.
I mean, you can either do
Yes.
that or the absolute value of phi divided by F star, either way, you know.
Yes. Yes, I think it's not coherent with what I wrote before. But in any case, the definition is the same as for the scalar CQ. Okay, so then we can write the equations of motion in terms of these program variables. They take this form, right? And then what we do is so we have second order differential equations, and what we want is to write these equations as a set of first order differential equations, such that then we can apply the evolution algorithms that Jorge has explained this morning, right? So what we do, no, if you write the equations of motion in this way, you can like write this, no, these two terms as the time derivatives of some combination of functions, right? So in a natural way, what we do is to define the conjugate momenta for the complex scalar plus a to the 3 minus alpha, the time derivative of phi. This is the same as for the scalar singlet. But then for the gauge field component, we define the associative conjugate momentum as a to the 1 minus alpha, a to the 1 minus alpha, ai prime. So note that the conjugate momenta for the scalar field and for the gauge field is different. They have different overlaps of the scale factor. This case a to the 3 minus alpha, this case is a to the 1 minus alpha. And this is related with the different friction terms that appear in the continuous equation of motion that I showed at the beginning of my talk. And then this way, with this transformation, you can just write this system of equations as a set of four four first order differential equations, where the kernels for the complex scalar and for the gauge field are written in this way. And then in this way we can just directly apply the evolution algorithms, like the velocity Verlet and Stagger-Heathrow. The same we can do for the second Friedmann equation. There is the kernel of we call B as the time derivative of A, and then we can decompose so we can write the second Friedmann equation as a first order differential equation, where the kernel of the scale factor is solved by all the energy components. And we can also write the constraint equation given by the first Friedmann equation in terms of program variables. Okay? And here AK of phi, AG of phi are the complex scalar, the kinetic gradient energies of the complex scalar. AK of A, AG of A are the electric and magnetic ones associated to the gauge field, and E of B is the potential. And these are volume average over the entire lattice. So basically now, so we have done this in the continuous. Then in the discrete, what can we do? Then we can directly apply the U1 toolkit to this in order to discretize the kernels and the energy component, right? With equivalent expressions in the lattice that are one gauge invariant and two I recover the continuous expressions up to second order. And basically, you just inspect the kernel and you just you identify all the operators, right? All the derivative operators, and then you just substitute this by the corresponding expressions in the you want to read. Right? And note that all of these terms are not written in terms of links. They are written in terms of gauge field, because as we are going to work in a non-compact formulation, these terms only depend on the gauge field component. Right? And now we can solve them with an appropriate evolution algorithm. In CosmoLattice right now, I think there are two algorithms implemented for gauge field. One is the staggered leaf algorithm that starts in such a way that the field components, so the field amplitudes and the scale factor are defined at a certain time, but then the momenta associated to these components are defined initially at at minus time step over 2. Right? So we know them, we know the field components and the momenta at different times. Right? And then what we do is to evolve them, just applying directly the staggered leaf algorithm. As we have done for scalar singlet, for scalar theories, the only difference now is that we have more equations because we have more fields. And yeah, I think the key point is that we have in this staggered leaf algorithm, we know the field components and the momenta at different times. And then we can also develop a velocity velvet algorithm, also mimicking the same that we did for scalar theories. In this case, initially, we know both the field amplitudes and the derivative and the momenta, at the same time, and the velocity velvet algorithm is exactly the same as for scalar fields, but the only difference again is that we only have more equations than before. And this is for VB2, so the second order velocity velvet algorithm, but this can be generalized to velocity velvet algorithms of higher order, and in fact, from 4th order to 10th order, are already implemented in CosmoLattice. So if you are interested in learning how these algorithms work, I just forward you to with the theory review. There's the theory review where this is explained in detail. And then let's discuss a bit about initialization, because this is quite subtle and it's not as easy as for scalar singlet. So for complex scalars, let me drink water again. So a complex scalar is just a combination of two scalar fields. So basically we can impose the conditions, the initial fluctuations, in the same way as we did for a scalar singlet, right? We just impose a homogeneous mode, which is going to call phi star, right? And then we just impose some fluctuations, all right? I mean, so then what is this spectrum of fluctuations, right? So in principle, we could try to set the same spectrum of fluctuations that we did for a scalar singlet, right? As we discussed in lecture 2, we were setting the fluctuations of the scalar field as a combination of a left-moving and a right-moving wave, right? Where its wave is composed by an absolute value, which is given by a Rayleigh distribution with an expected root mean square, and then an exponent of a uniform random phase. And the fluctuations of the time derivative are given by the derivative of the previous expression. So if you see these expressions, we have each field depends on 4 random functions, right? That change arbitrarily throughout the lattice. So we have 4 for each scalar field. As we have a 2-component scalar field, we have in principle 8 random functions for each complex scalar. Okay? What is the problem? I will see it now. Now let's focus on the gauge field. Then I will let you know what is the problem. For gauge fields, what we do is to set the gauge field exponent to be exactly 0 at all points of the lattice, and then the time derivative of the gauge field, which is the electric field, we only give with fluctuations. So only fluctuations, it doesn't have a homogeneous mode. So this means that in our simulations, in CosmoLattice, initially we have some electric field given by these fluctuations, but we don't have magnetic field, because the magnetic field is just a combination of special derivatives of the gauge field components. So we have some electric field, but we have no magnetic field inside. And how we impose these fluctuations to electric field? Well, we go to the Gauss constraint. The Gauss constraint, as I have said, must be preserved at all times, but it must also be preserved initially. In fact, you need to make it preserved initially, that it's preserved during the entire evolution. So what we do is to take the Gauss constraint, which is this one, we apply a Fourier transformation, right? And after being Fourier transformed, it can be written this way. And then we isolate a dot, the a dot I, so the time derivative of ai, and we can use this expression to impose the initial spectrum for the electric field, right? So we have basically what we do is we have the complex scalar which fluctuate throughout the lattice. This imposes through this expression fluctuations on the current, on the initial current, right? We plug it here, and this generates fluctuations on the electric field. How we do this in the discrete? Okay, so now in the discrete, remember that we need to, as I emphasized in my first lecture, we need to choose coherently the momentum or the lattice momentum with our choice of a special derivative. So in our discrete formulation, this is the Gauss law, right? And in the Gauss law, we are using this charge special derivative with the minus sign here. And this is in position space. When we go to momentum space in the lattice Fourier lattice, here we must choose the correct lattice momentum. All right. So the lattice momentum associated to this choice of the special derivative. And if you go to the first lecture, this one is complex. It's a complex momentum. All right. If not, it will not work. So if we have here another special derivative, here we will have another momentum or another lattice. And as I have said before, we want. So what is the problem? The problem with the scalar fluctuations that I was mentioning before. When the issue is that we want a zero electric charge in the lattice, as I mentioned before. So we require that the charge, which is given by the integral of the current throughout the lattice, and then it's given by this, and the real part of this product, you just substitute the expression of the current here, you can obtain this. So we want this term to be 0. Right? And this is not, and if you let the 8 functions, the 8 random functions of the initial amplitudes of the complex scalars, you let them arbitrary, so independent, then you see that this is not in general whole. So what we did, what I did in my PhD thesis is to realize that if we impose 3 constraints to these 8 random functions, right? In particular, if we set the amplitude of the left wave to be equal to the right wave for both components, and then we set this relation between the phases, with the 4 random phases, then with this choice, so by imposing this, we have indeed always a 0 initial current. So in reality, we don't have 8 random functions specifying the initial fluctuations of the complex scalars. We only have 5, because the other 3 are imposed through these relations. And just to end the presentation, I'm going to show you an example of an abelian Higgs model. is formed by this action, by this potential, this lambda phi to the 4 potential, where phi is the absolute value of the complex scalar. And then this is analogous to the scalar case scenario that we studied this morning. So I'm going to choose program variables that are equivalent. So I set f star to the initial amplitude of the complex scalar. I set the initial frequency to be the initial I set omega star to the initial frequency of the oscillations, and alpha I set it to 1 to have conformal time. And then I can compute the program potential and I see that it is phi tilde to the 4. It can be phi to the 4. So, and then in principle, you can you can basically, if you give initial amplitude to the complex scalar, what you can basically distribute this initial amplitude throughout the components. However, what I'm gonna do is to give the same initial weight to the both components of the complex scalar. But you don't need to do that in principle. So the way in which a model like this is implemented in CosmoLattice is very similar to what we do for a scalar model. We just need to specify the number of fields of each species that we have. In this case, we have one complex scalar, one abelian gauge field, and one potential term, which is lambda phi to the 4. Then we need to add a line, which corresponds to this function called couplings manager. Basically, this function deals with how which complex scalars are coupled to the one gauge sector, because we can have, in principle, we can have complex scalars that are not coupled to gauge fields. So we need to call this function and activate it to true. Just to let me clarify that this model file is also given by default in CosmoLattice. So I mean, you should have it. If you have downloaded the code, you should have a look. Then, as always, you can also set the initial norm for the complex field, for the absolute value of the complex field and its momentum. You can also set the charge QA and the abelian extent GA, right? And also the parameter lambda of the potential. Also, this parameter file is provided with the code. And then we can this is in the input file, but then in the model file we have this complexify function that basically what it does is this initial homogeneous component just distributed in a certain way between the components of the complex scalar. All right. So, for example, this reads the initial amplitude of the complex scalar and assigns it and basically distributes it equally. So that's why we are including this square root of 2 in both components. We also define the program variables in the same way as for the scalar singlet, and we also need to write the derivatives, the potential terms, and the derivatives with respect to the complex scalar. Right? So we have 5 to the 4. So we need to include the first derivative, which is 4 times phi cubed, and then the second derivative, which is 12 times phi squared. We are with these functions. I'm gonna skip this, and basically, this, if you run this model, this is all the output that gets produced, right? So what do we have? We have we obtain, for example, the volume average of the norm of the complex scalars, then also the volume average of the real and imaginary parts of the complex scalar, the average norm of the electric fields and magnetic fields, and their variances, the different energy components. Also, the code monitors how well the Gauss law is preserved, right? So basically, it takes the Gauss law and checks if the left-hand side and right-hand side of the constraint is are the same. Right? And then we also plot the spectra of the complex scalar and the Gauge field. So this is of course in detail, explained in detail in the manual. So you don't need to recall which what each file is printing. So let me emphasize that in the abelian Higgs model, I'm going to show you now the results of the simulation. But let me emphasize that in the abelian Higgs model, you focus on the gauge fields. You have a source term, which is given by the current, which is given by this expression here, and this current basically contains the term phi squared a of I, right? And this term is identical or very similar to the source term of the analogous scalar equation that we have simulated this morning. Right? So before, in the equation of motion of the Dotter field, we had phi squared chi, and now in the equation of motion of the gauge field, we have phi squared ai. Right? So this means that gauge fields coupled to charged scalars with a monomer potential experience parametric resonance, and in fact, the qualitative details of this parametric resonance is very similar to the scalar case that we have seen in lecture 2. And in fact, we did explicit comparisons between the scalar and gauge simulations in this paper. You want to have a look.
Paco, I see there is a question. I don't know if you want to take it now or we wait, because there are a couple of questions also in the chat, or we wait for you to finish and then we.
So I think I have only 3 slides remaining, so I think I can finish.
Sure.
And then we answer the questions. Very well. So now I'm gonna show the figures of this simulation. This is, for example, the evolution of the energy density component. Red is the electric energy, orange is the magnetic energy. You can notice that as I have commented before, we initially already have electric energy. This is due to the way that we impose the initial fluctuations, right? We were imposing electric fluctuations only to the electric field, but not to the magnetic field. So the magnetic field starts up here. Okay? And we see the same effect than for the scalar model we simulated this morning. We just see an exponential growth of the energy transferred to the gauge field, which then eventually becomes of the same order of magnitude, or comparable more or less, with the energy of the homogeneous inflaton that is oscillating, and then we start there is back reaction and the nonlinear regime starts. One interesting thing is that, as I have said before, here we check that if the Gauss law is preserved throughout the evolution, and in fact, this Gauss law must be preserved up to machine precision. This is not like the energy. When we were taking the energy conservation before, we had a certain degree of violation of that law, right? Which is depended on the time step and the algorithm you were using. In this case, the Gauss law must be preserved always at all times, because we have imposed it in our lattice formulation. Right? So if you check, this is the evolution of the Gauss constraint as a function of time, you can check that initially that it doesn't seem like it preserved up to machine precision, but this is because we have a very large homogeneous background over which we have very small fluctuations, right? So after this happens, and we achieve the completely nonlinear routine when the homogeneity of the inflaton has been destroyed, we see that it is preserved up to 10 to the minus 12. So this is compatible with machine precision. So yeah, if you have what I mean with this is that if you do a gauge simulation and you have a violation of 10 to the minus 2 or 10 to the minus 3, it's wrong. There is something wrong there, and you must find out why. What? And finally, this is my last slide. These are the spectra of the electric field, the magnetic field, and the complex scalar. And you can see that there is clearly an initial resonance band, right, which is analogous to the resonance band that appears on the scalar simulations. And then eventually, there is red scattering, and the spectra widens, right? Becomes wider, and yeah, we must ensure that in this simulation we also capture well the ultraviolet routine. And I think with that have finished, and we can proceed to the questions if you want.
Thank you very much, Paco, for being on time. Okay, so yeah, thanks a lot. Pankaj, you have a question, please. Can you go ahead?
Yes. So I have a very naive question. So, so in this example, you have said that you have one U1 gauge coupling, so it is coupled to the complex scalar. So suppose in my model, I have one more U1 gauge field, like say U1 prime or U1x or something with charge. So how do I specify this gauge charge and this gauge field to my model? And if I want to study this inflation in this type of models with two different gauge
one second.
charges.
I think the sound has interrupted for a while. Can you repeat? Because I think I have problems with my headphones. Sorry.
Can you hear me now?
Yes, I can hear you.
Yeah. So my question is that in this example, you have shown only one U1 gauge field and how it couples to this complex scalar, and then you have shown these evolutions. So my question is, like, suppose I want to model a physics model. So I have two gauge fields with two different gauge charges, say U1 and U1 prime. And I want to study this inflation phenomenology with this kind of models. So how do I specify my gauge charges and how do I specify my gauge fields in the model template? And how do I tell my model file these specific gauge charges and their physics?
So I think what you need first is to change this from 1 to 2, right? This NU1 fields to 1 to 2. And then I think this function allows you to specify which complex scalars coupled to U1 H field. I don't remember right now how this function works, so I will need to check. I think Adrian is here. Perhaps he can help me with that answer. I don't know if he has just connected. So.
Hey.
Hello.
I just heard that I had to give the answer.
Oh no, yeah, okay, you have just connected. No, I have received this question of how to simulate two gauge fields instead of two abelian gauge fields instead of one. Right? So I was mentioning that in the model file, of course, he needs to change this U1 to 2, right? Because you have two gauge fields. But then I think you also need to perhaps.
You need
to play with this complex manager function, but I don't remember right now the syntax.
And also you need, by default, we deactivated it because we never tried that it was actually working. So, so if you try to do it, you're gonna get an error message that is gonna tell you where you should go uncomment the error if you want to play with it. In principle, it should work, but we never tried it really. So.
Yeah, that's right. So for now, the current version of CosmoLattice has only been deploying with one abelian gauge field. That's true. I completely forgot. Okay. Theoretically, it should work with more than one gauge field, but we never tested it. So when you
meaning it compiles, it runs, and it doesn't make nans, but we never checked that the physical result was correct.
Yeah, exactly. So we never
actually. I was more curious about how do you transfer the charges of different gauge fields to these model files so that it can read the physics out of it. So, but anyway, okay, thank you.
Sorry, so you mean how? What do you mean exactly?
I was telling like, suppose this example has one U1 gas field. So suppose I want to model, have a model in my mind, suppose with two different gas fields with different gas charges.
Yeah.
Say U1 prime or U1 B minus L kind of model.
Yeah.
So how do I tell this CosmoLattice that I have two different gas fields with two different gas couplings, and how do I try to understand this? Suppose inflation in the inflationary scenario in this kind of model. So how do I tell or write the?
Yeah, so if you what Paco was explaining it is how to write the model with more than one gauge field. You need to change the number of gauge field here, and you need to add this parameter true tells you whether your scalar field couples to the gauge field or not. So if it couples, you need to put 2 times true. Exactly. And then in the input parameters, there is a common that takes, I believe, one that takes the charges of the field and one that takes the coupling strengths of the gauge field.
Do you have the input parameter example there, Paco? Yes.
Yeah, exactly.
Yeah.
It's here.
So if you have more than one charges, you just add numbers there. So if you have, let's say you have one field and 2 gauge field, you add 1 G basically.
I see. Yes. Thank you.
It's not tested in any way, as we said, so
yeah.
Obviously CosmoLattice gives you the ability to do that if you want to, but so far we didn't bother, to test it with any particular scenario. So it would require you to know how to handle well CosmoLattice for a while before maybe you jump into modifying that, but it should be possible,
And yeah, and you have a 50% chance that it works. So just need to test it.
Yeah, but at least
so let me play with it. Then I'll I'll get back to you if I made some progress and get to see.
Sure.
Yeah, that'd be interesting if you can test it.
Yeah. Okay. Thank you.
Okay, thanks. More questions from Antonino?
Yes, thank you. The question is for Adrian, actually, because from this morning, when trying to plot the results from the runs, I managed to do that with Mathematica, but for the Python routine, it gives me an error. It says that it doesn't find LaTeX, but I have also downloaded the basic tech. So I don't know which version of LaTeX do you need to.
You can just comment whatever. So yeah, you can just remove the. At the beginning of the Python script, there is probably a bunch of comments that are just there to make the plot nice. You can just remove them and the plot will look less nice, but it's not going to use LaTeX.
Okay.
Or the thing with this RC param or whatever, that they are just there to make the plot nice.
Okay.
Okay. The VCAP, please.
Hello. Yeah. So my question is, you said that in this code you set the initial value of AI to be 0. So is that compulsory, or is it possible to change that initial condition also?
I mean, you could change it. In CosmoLattice, we just do that. We just set AI to 0. But so you want to change that, it would require you to know a bit more, you will to know a bit what's happening behind CosmoLattice. So you will need to go to the files and change and play a bit more, play with the code just to change whatever you want. But in principle, no, there is no parameter that allows you to set fluctuations to the magnetic field.
Oh, okay. So it is not like I can change it in the input file or anything like that.
No, you can. Yeah, you cannot change it in the input file. It's not a parameter. You will need to edit the code itself.
Okay.
Yeah, it's more of the gray box level that we were discussing yesterday, but of course it's completely feasible. And it just depends on the scenario. The reason why we did it the way we did it is because it's a very simple generic manner to deal with quantum vacuum fluctuations on the gauge scalar sector, such that the quantum fluctuations are at the level of the scalar field through the spectrum, and then we read off through the Gauss law the electric fields from that, and then we start creating the magnetic fields from the iteration in the equations of motion. But of course, if that's not compatible with your physical setup, then you will have to modify CosmoLattice, because once again, please understand that the fact that we have, set up for certain scenarios a given procedure for initial conditions is not a rigid thing. Okay, you really have to think of CosmoLattice as, again, a platform where you can implement whatever initial conditions you want, and in principle, whatever evolution you want. Okay, and what we are presenting here are the basic examples that apply to a whole, generality of circumstances, but not necessarily all the time. And if you have a magnetic field present in your simulation at the beginning, you are going to have to deal with that. But that requires editing of the. You see, we cannot provide that you guys write one line in the input parameter and it does magic of everything. This is not possible. So essentially, what we have to do at the end is make choices for basic cases. And then if you need something more elaborated, you need to go into seeing inside the code how it works, and then what you need to change in order to accommodate for that extra initial condition.
Okay, thank you.
More questions. Alessio, I think you were having pretty much the same question, right? Yeah, essentially it's for convenience, but and because here we are thinking of situations where all the fields are in vacuum, the fluctuations are in vacuum initially. But in other circumstances, you may want to do differently. And actually, in action inflation simulations, we had to play a lot with modifying all this procedure. So at the end of the day, if your physics required to change the prescription we just set up, then yeah, you have to do it into editing the actual initial conditions in CosmoLattice. And by the way, this prescription we did for the initial condition is particularly convenient for non-abelian. Okay, because for non-abelian gauge fields, the covariant derivative of the electric field in the Gauss law also involves gauge fields, amplitudes, through the nonlinearity of non-abelian structure. And if they were not zero, then you will have to take them into account there for consistency of the Gauss law, which would make it way more complicated. So it's just a convenient trick that it's been shown that for those scenarios where you start from vacuum fluctuations, it plays no role, and then it reproduces the correct physics.
I think there is another question.
Yes,
From Anna?
Yeah, please go ahead. Yeah.
Hello, can you hear me?
Yes.
So far we have considered scalars and gauge field, and how about fermions? Is it possible to investigate fermionic reheating using CosmoLattice?
Well, not really, because fermions have this Pauli blocking, such as the occupation number cannot be larger than 1. So this means that we cannot ignore their quantum nature, and then the lattice, we cannot do lattice simulation for fermions as we are doing with for scalars, because we cannot assume that they can be approximated by continuous functions as we are doing for scalars. So the lattice approach, as we are doing here, wouldn't work for fermions.
Yeah, just to add on this, presumably you could do the linear regime of parametric excitation of fermions, which is known that instead of pushing the occupation number to grow, what it does, it propagates more power into the UV. Okay, and there are papers that study this analytically and numerically with Mathematica in one dimension, but then it would be a waste of resources of the lattice to do that, only for a linear regime. What you cannot do is the back reaction. The real interest would be to do the full quantum evolution of fermions coupled to gauge fields or scalars, and this we cannot do, at least as all of this is written. And we cannot do it, neither anyone else, to my knowledge. There is no technique to do this easily. Okay.
I see. Thank you.
More questions. Yeah, and I guess your hand, I can. Yeah, very good. Thanks. Yes. Ali Reza, you had a question on inflation. You want to ask this question?
Hi.
Hello.
Can you hear me?
We do.
Yes.
Yes. Thanks for your school. It's very nice. So I have a question about the simulation of, for example, power spectrum of a scalar field during inflation. I want to, for example, get the power spectrum of a scalar field and put this power spectrum to another code, for example, CosmoMC or CMB fast to simulate our universe. So I need to know the power spectrum of a scalar field at the end of inflation after the 60 fold. So I think I have to change Tmax to be very large to have a 60 fold of inflation. So am I correct, or there is some?
No, the problem is, yeah, I don't know how to explain you this, because I think you have maybe yet a misconception about what the lattice can do, okay? When you are comparing to these other codes of CMB, you were saying, what those codes do is a propagation in an isotropized universe, you know, where you discretize a grid of momentum in 1D, okay? And then they can do arbitrarily separated scales. But in the lattice, because we are in 3D, our separation of scales is very limited, okay, because of memory. So essentially, if the fluctuations that for which you want to compute the power spectrum during inflation disrespect linear physics, the first observation is there is no point to do a lattice simulation, okay? Because you can do it with other techniques, and you shouldn't waste the resources of doing a lattice simulation for that. But secondly, even if you wanted just to do lattice simulation to test, let it be a linear regime, or the real interesting thing would be the nonlinear physics, which is what you cannot do otherwise without the lattice, then you are limited to a finite range of scales, or in other words, a finite number of e-foldings. Essentially, it's not a matter of when you set up the final time scale. It's a matter of understanding when you can start your simulation that you are abandoning the linear regime, and when you finish it, how long afterwards you can finish it during the nonlinear regime in a given scenario. And that's going to give you the evolution of your field fluctuations, which you are going to have in the form of a power spectrum, for instance, for the finite range of momenta that you can really simulate in your lattice, which typically spans 3 orders of magnitude, no more. Okay. So you see, it's very difficult to answer your question because I don't know what you have in mind, but typically, imagine I have some nonlinear physics that gets activated 40 e-folds before the end of inflation.
Yes.
All right. So what you should do is like 43 e-folds before. If you know 40 e-folds before the end of inflation, you are going to hit nonlinearities. Now, say some few e-folds before, you set up your initial fluctuations at sub-Hubble scales in your simulation. And then these are all going to get excited. They are going to cross the Hubble radius and get super horizon. But at some moment, you know, if your nonlinearity requires to couple these guys to further UV scales, this is not going to be possible. So you are only going to be able to transport these initial sub-Hubble modes for a finite number of e-foldings. And so it's very complicated. It can be done. It's been done by our group actually in Action Inflation, and it'll be the topic on Friday. But it requires you to understand very well your inflationary scenario, the time scales, and the ability of the lattice, the limitation of the lattice in terms of separation of scales. Once you understand all of that, which from your question is not clear to me, you have all of that under control, then you can do something with the lattice, but it's extremely complicated, unfortunately. Yeah.
Thank you. Thank you.
No problem.
Good.
Unfortunately, the lattice is very, how to say, very beautiful that it can do nonlinear physics that you cannot do analytically, but it's limited to the fact that following three-dimensional distribution of fields is very costly. And then you cannot do arbitrarily separation of scales. You are always limited, unfortunately. We wish, you know, we could do arbitrary separation of scales, and you could simulate the whole 60 defaults of inflation, which would amount to separate 28 orders of magnitude scales, you know.
Yeah. Good.
On the other hand, for majority of inflationary models I know, you don't need to cover all the inflationary e-foldings precisely because if the physics is linear, there's no need for the lattice simulation, and you should only cover once the physics becomes nonlinear, as is the case, for instance, in axial inflation.
I see. Thank you. Thank you very much.
No problem. My pleasure. More questions, guys? Maybe something related to the code as well?
Is there anyone who has not been able to compile and execute the code?
That's a good question, yeah. Can you raise up your electronic hand if you didn't succeed in running the code? Just to know how many of you are having this trouble. Oh, apparently everybody.
Either everyone has been able to run the code or they are not saying it.
It's not clear to me, the lack of answer, you know.
Yeah.
Well, if you don't have questions as of now, feel free anyway to, you know, put your questions in Slack about the code or problems you may have with the running. Typically, these are basic things. And for those of you who are asking like a more evolved use of CosmoLattice, yeah, I think the best answer is like, you first need to understand how the lattice works and how the code works, and that requires a lot of time. And it's not immediate. You're gonna jump into a more complex scenario if you don't control basic scenarios first, you know, because as said, lattice is difficult and limited, and one needs to understand these limitations and how it works internally. Okay, shall we leave it here, or is there any other question? Code or theory related? Okay, I see no more questions. Then we'll see you tomorrow, guys. Thank you very much for attending.
Thank you.
Bye-bye.
Thank you very much. Bye.
Thank you, guys.
Thank you.
I don't know how to stop sharing.
Mm-hmm.
I have the problem that when the commands disappear, then I don't